The next speaker is Wai Gao. It's from Stony Brook. We'll be speaking on the success-based learning procedure.
Thank you.
Thank you.
So I'm very happy to present my work to you. So my topic is a success history-based learning procedure to optimize server throughput in large-scale distributed control system. So it has three parts. The first part introduces the problem. Second part is our solution. And third part is the simulation result. So first, let's talk about the problem we're going to solve. Client-server problem with a dynamic server capacity. So first, let's have an overview of the rig control system. It consists of two layers. The top layer, console level, contains workstations and servers providing services to users for providing some general computing resources. And the lower layer is the front-end level, consisting more than 500 front-end computers, and each of them is running on VxWorks, a real-time operating system. And the problem lies in the front-end level. So in the rig front-end, every computer acts as a server, providing services to a large number of clients. However, when the number of clients reaches limits, the system tends to slow down or even crashes. And the picture on the right is an experiment we conducted to show the problem. So we increase the message rate linearly and observe that the system becomes slower exponentially. So that's a performance bottleneck in the front-end system. So what makes this problem harder is there are also asynchronous processes residing on the front-end computers, and those processes will share FEC resources when the information they queried is updated, so resulting in varying available server capacities. So one difficulty to deal with the problem is how to regulate the client's behavior so that they can learn server's limitations and adjust their strategies properly. And in this work, we consider this problem from a game theory perspective. So we model the problem as a repeated game, where a stage game is played over and over again. We divided the time into discrete time slots, and the stage game is played in each time slot. The stage game contains a set of n clients as players, and each player has two available actions, whether send their traffic or hold their traffic. And depending on the result of the game, if server crashes, client gets punishment value -C, which is also called server crash cost. And if the server does not crash, then clients get benefits value, which is equal to the amount of traffic they hold. It's Li for client I. And our goal is to safely and efficiently route client traffic so that server throughput is maximized and server crashes as little as possible. We formulate as integer programming with the goal to maximize server throughput. And the first constraint restricts that the server does not crash during the game. And the second constraint specifies the client's actions are binary value, with 0 standing for hold and 1 standing for send. The third constraint sees that the maximum traffic a client has is below a threshold. And note that one special variant of this problem is the server capacity does not change at all. Then we get a reduction from the knapsack problem, which is a well-known NP-hard problem. And along with this dynamic feature, make it very difficult to seek any optimum solution. So next, we propose our heuristic algorithm. So first is a regret-based procedure we applied we adopt and was proposed by Sergio Hart to give a basic solution. And then we propose our scheme to approve the basic algorithm to better accommodate the dynamic server capacity. So the basic solution is a discrete regret-based procedure. We apply it to regulate clients' behaviors to teach clients make a reasonable choice actions. So by applying this procedure, the clients will play strategies which are more profitable according to their history play. And the client can learn their environment gradually based only on their own information. However, it only works in a static environment where server does not change their capacities. To accommodate the dynamic capacity, we need to improve the algorithm. So let's have a brief review of the server crash cost. So it is a punishment value clients need to pay whenever server crashes. So intuitively, high crash cost will suppress client's intention to sending traffic, and a low crash cost will motivate client to sending more traffic. So our idea is develop a discrete scheme so that the client can learn to set their strategies properly in the dynamic environment. So more precisely, we accomplish this by modifying a parameter called the crash cost factor, denoted by alpha, and the crash cost for client I, CI, is defined as alpha times Li, which is the client's load. And so note that clients now have different crash costs, which are proportional to the amount of traffic they hold. So while applying this strategy, the client keep monitoring the amount of traffic they successfully load to the server, and we call it the amount of effective traffic. And whenever an increment occurs, the client records the corresponding value as a successful value. And the memory structure is like this. The first row stores the successful values, and the second row is the corresponding increment on the effective amount of traffic. And it's also called as a weight of the CCI value, and an index k used to update the memory. So the algorithm procedure goes as the following. Clients check their effective amount of traffic periodically, and whenever an increase is detected, they record the CCI value and the corresponding increment. And later, this value will be used to generate new values. So when clients need to update the new values with the probability p, they use the following strategy. So first, the client checks their memory is full now. If it's not full, then they choose a value from a predefined set randomly. And if memory is full, then they generate new values using the weighted mean of all the values in the memory. And with the remaining probability 1 minus p, clients choose a value randomly from a predefined set. So there are a couple of features help this algorithm to accommodate the dynamic server capacities. So first, client use the amount of effective traffic as a metric to update the parameters, so which helps them to optimize server throughput, as shown in the integer programming. And it also helps preserve the chain of changes of the values due to the varying server capacities. And second, clients always have a chance the probability 1 minus p to explore new values, which helps them to adapt new server capacity changes. And third, clients use a weighted mean to generate the new values. So more profitable values will have a larger impact to the new generated values, which facilitates the algorithm convergence rate. So we should expect a better performance than the basic regret-based procedure. So we conduct a simulation with 500 clients and server. And each client sending one message per second to a server, and the server changes capacity every 3 hours. And we conduct a simulation with the simulation length 12 hours. And this picture shows a comparison result of the effective amount of traffic. So the red line is the server capacity. As mentioned, the server changes 4 times capacity. In period 1 and 3, the server have a lower capacity, and 2 and 4, they have a relatively higher capacity. And first, let's look at the case when there's no regulation on client's behaviors. So when there's in this case, the client will send the traffic all the time, so that the actual amount of traffic from them will be always greater than the server capacity, as shown on the top line. So server crashes all the time, and no traffic successfully routed to the server. So resulting O0 effective amount of traffic is shown in the bottom line. So on the other hand, if we apply either the regret-based procedure or the success history scheme, the client can learn the environment and adapt their strategies properly to the server capacity, to the environment. So we observe the effective amount of traffic improved significantly. Moreover, the success history scheme helps the client better learn the environment and so makes them adapt faster to the capacity changes. So we have a higher effective amount of traffic. It's shown on the green line. And next is a comparison result of the server crash percentage. So as I mentioned before, the server crashes all the time when there's no scheme at all. It's the downward spikes the server crash time, and if there is no regulation, the server has 0 alive time all the time, as shown on the bottom line. And if we apply both either of the scheme, we can see the crash percentage is reduced a lot. And moreover, with the success history scheme, it results 60% less crashes than the basic regret procedure. And the next is the count of % for every client. It's the number of times the client chooses to send their traffic to the server. It indicates how equally the server treats the request from every client. So with the success history scheme, we can see a 45% less variation. This is a table with data collecting from each capacity period and the whole simulation time. In period 1 and 3, where server has lower capacity, both schemes crashes the server with a small percentage of time. But the success history scheme result much less crash probability and also a higher server throughput. And on period 2 and 4, where server has a relatively higher capacity, both schemes are safe to the server. And the success history scheme has higher effective amount of traffic. So which shows our proposed scheme can help client adapt better to the server capacity changes. And also on the right bottom chart, we can see the standard variation is almost 50% less in the success history scheme than in the regret-based scheme. So it helps to promote a more equal user experience. So conclusion, in this work, we analyze a real-world performance issue in a rate control system. We model it as a repeated game and formulate an integer programming and point out its difficulty. We provide a basic solution by adopting a regret-based procedure and improve it by proposing a success history scheme to better accommodate the dynamic server capacity. And the simulation results show that both schemes can significantly improve system performance. And moreover, compared with a regret-based procedure, the success history scheme can result in a notably higher server throughput and a lower crash probability. Thank you.
Okay, we have time for questions.
I didn't get it maybe, but why does the server crash? I mean, what is a crash for you?
Because the client will keep sending traffic to the server, and so server can't handle that amount of traffic, so it becomes slow down and crashes.
No. There.
Have you considered a publish-subscribe scheme with multicast? I mean, this would immediately eliminate the problem that the more clients you connect, the slower the server gets.
Sorry, I couldn't get the question. Can you repeat?
If you have a publish-subscriber scheme and the server does a multicast to all the clients immediately, you would get rid of the problem that the server is slowing down if more clients are connecting.
So in our system, the server and the client behaves if the server respond only after the client send a request, and this is one way. And the second way is the client first send a request, and whenever the information updated, the server will notify those clients. So I don't know if the multicast will be possible in the system. So if client asks the server at the same time, then we can see it's kind of a multicast. But still, if too many numbers clients are asking the information, the server still can't handle. I hope I answered your question.
Any other question? No? Okay. Thank you again.